Okay, so Maddie is going to have his TA hours, office hours, whatever you want to call it, in the upstairs room above the dining area in Newcastle, if that's what I'm thinking it is. Wednesdays 5 to 7, so tonight, but obviously not next Wednesday. And then continuing on from there. So if you can't make my office hours or you're scared of me, or anything like that, go and see him. I bet those hours are probably more convenient than mine. Any questions on stuff from chapter 6 we already talked about? This is going to be a pretty short day, so I have a ton to cover. Um, so we talked about acid base equilibrium. This is last time. We did REO, predicting the acidity of compounds without using pKa values. And so today we're going to talk about kind of like the practical application of that kind of thing. So how do we pick specific acids and bases to use in our chemistry? So if we take a kind of a general reaction like this, we could have something like this where we have the ions are the base and the conjugate base, so anions. Or we could have, right, and this depends entirely on what the identities of A and B are. Or we could have a case where there we go. Where the ions are cations, and in that case, then we have the acid and the conjugate acid as our ions. And so regardless of what A and B are, have said stablest, but well, the equilibrium will favor the side of the equation with the more stable ion. So, for example, when we're talking about the REO examples, generally speaking, we're looking at the base when we do REO rules. And so then we're looking to see whether B minus or A minus is a more stable base based on atom resonance induction orbital. So when we're actually picking individual reagents, we just pick a reagent that pushes the equilibrium in the direction we want it to go. And generally speaking, you'll have a wide range of things to choose from. And at that point, you then have to look at stuff like solubility and cost and just general ease of use. But there are going to be some cases where if you've got a reagent that's very resistant to, if you've got a very weak acid or a very weak base, then you have to have a very strong, complementary reagent in order to get that weak chemical to react. So let's say that we have let's say we have acetate. So let's ask So let's say we have the acetate ion in solution, and we would like to protonate it to make acetic acid. Acetate's going to be our base, and so we need an acid to donate a proton to the base to make our conjugate acid, which is acetic acid. So what acid can we use? Um, well, let's see if, well, we know that water is amphoteric, so it can be an acid or a base. So maybe water is a good acid. It's certainly the cheapest one. So let's try that. So we're going to write out an equation just like we have been with acetate as the base and water as the acid. So acetate plus water, and we're going to have an equilibrium of unknown here. There's acetic acid, our conjugate acid. And hydroxide is our conjugate base. So the first thing we want to do is try and use the pKa table. That's preferable to doing REO, mostly because you just look at the table and it tells you the answer. Okay, and so for pKa, the equilibrium is going to lie on the side with the weaker acid. So we need to look at our two acids, acid and conjugate acid. And then we need the pKa table. And okay, so acetic acid is right here. And it has a pKa of 4.75. And then our other acid is water. And if we look on our table for water, there's water. pKa is 15.7. So lower pKa means stronger acid, higher pKa means weaker acid. And so water is the weaker of these two acids, and that means the equilibrium is going to lie on that side. All right, so already this is not looking good for our reaction because we want the reaction to go forward. And the equilibrium is telling us that it's not. So at this point, right, we can make our conclusion. Water is not a good acid for protonating acetate. But let's say that either the pKa table was sort of inconclusive, doesn't usually happen. More often, what'll happen is you'll look on the pKa table and there won't be a molecule on the pKa table that looks like your molecules that you're dealing with. If we had, if they were just very slightly different, like we had um, an extra methyl group or something, then we can say, all right, the pKa of that acid is also going to be 4.75, basically. Um, but if we don't have structures that are anywhere near similar things to what's on the pKa table, then we have to use REO. And so we can also use this to check our work. Really just more stable base. Okay, so now we're going to be comparing acetate with hydroxide. A is for atom, So in this case, both of the negative charges are on oxygen. So that makes atom not a useful way to tell them apart. R is for resonance. So we need to see if the bases or conjugate bases, whatever you want to say, have resonance stabilized negative charges. We can draw a resonance structure of the acetate ion like that. Okay, that would give us this. However, hydroxide, we can't draw a resonance structure of that. So that means that acetate is the more stable base, and the equilibrium favors the side with the more stable base. And yes, that is what we already concluded. So looks like our work was correct. Okay, what other acid should we try? What's an acid that's like a real acid? HCl? HCl is a good acid. Hydrofluoric acid. Okay, so we'll do the same thing here. Acetate plus HCl gives us acetic acid plus chloride. So first we'll look at pKa values of the acids. Acetic acid, we already established that that is 4.75. And the pKa of HCl up here is -7. Okay, equilibrium is going to favor the side with the weaker acid. The weaker acid has a higher pKa, stronger acid has a lower pKa. And so, right, this is plus 4.75. And so the acetic acid is the weaker acid. So that means our equilibrium is going to favor side with the weaker acid. That's the acetic acid. Okay, so this is good. Our reaction seems to be going forward. So that kind of tells us that HCl probably is a good acid for protonating acetate. But let's check our work. Let's use the Ario method. Okay. First is atom. So we're looking at the bases in this case. And we're going to compare oxygen for the acetate ion with chloride, right? So look at our periodic table, and then we run into this problem where they're not in the same row and they're not in the same group. So in this particular case, we're going to say that the ARIA method is inconclusive. And so the pKa is going to be the way that we figure out the answer for this one. So this is why I say to use another reason for why to use the pKa table first, because if as long as you've got molecules that are somewhat similar to the things in the pKa table, which will be a lot of things, you don't have to worry about that potential issue with the ARIA method. So this is really only going to come up when you've got something like an oxygen versus a chlorine, or a nitrogen versus a sulfur, or something like that. This is probably the best example of that sort of thing. So if we went in the lab and we have a sample of acetate and we want to protonate it to make acetic acid, HCl would work. It's got a lower pKa, and this is sort of the fast way to do it. It's got a lower pKa than acetic acid, but water does not. And so really we can just look at the conjugate acid of our base of acetate, say, okay, that's 4.75. And so all we need is an acid that's got a lower pKa than 4.75. So that means that any of these acids will be sufficient. Okay, so sulfuric, this protonated ketone, which it's not really something you have in a bottle very often. HCl or hydronium, which is just a generic aqueous acid. Strong aqueous acid. All right. Another thing that we have to keep in mind is called the leveling effect. And this has to do with solvent. So we really, so far, haven't talked very much about solvent choice. But the leveling effect says that the base that we choose cannot be a stronger base than the conjugate base of the salt. Same is going to be true for acids, but we'll see that in a moment. Base is more common issue. So this is a common base in organic chemistry. It's called N-butyl lithium. It's a really strong base. It's good for well, a whole bunch of things. But let's say that we want to be able to use this base, and I don't know, our molecule that we want to deprotonate is dissolved in water. And you'd say, okay, we'll just add our base to the water, and then we can do our chemistry. The problem is that when you add any reagent to a solution, it has the potential to react with your solvent. And so right here in our acid-base chemistry, we can make up a reaction and then see if it's reasonable by looking at the position of the equilibrium. So, all right, so this is our base. Water will act as our acid. So butane is our conjugate acid because we get that four-carbon chain with the lone pair and the negative charge. That's our proton acceptor. We accept a proton from the acid. Okay, and the acid becomes hydroxide, which is our conjugate base. Okay, so the rule is that the base used cannot be stronger than the conjugate base of the solvent. So we're talking about bases here, so we're going to compare the base and the conjugate base, or we can compare the acid and the conjugate acid. Essentially, we just need to look at this equilibrium here. So why don't we actually do the pKa's of the acids? Okay, the pKa of water is 15.7. What about the pKa of butane? Well, we have an alkane down here at the bottom. This one in particular is ethane. Pretty similar. So we can just say that the pKa of butane is roughly 50. So the weaker acid is butane, not water. So that means our equilibrium is going to lie on that side. Okay, we can also check that by looking at REO. For REO, we look at bases. And first rule is atom. All right, so in the bases, we're comparing oxygen with carbon. And oxygen is more electronegative than carbon. And they're in the same row. And so this is the more stable base. And so that means our conclusion is correct. The equilibrium lies on that side of the reaction. So this is a problem because if we want to use N-butyllithium to react with something else in our solution, it's not going to have time to do that because it's first going to react with our solvent because the solvent is present in really high concentration because it's literally the solvent. And so if you try and do this, if you add butyllithium to water, well, first of all, it will explode, uh, which is this reaction. It's extremely violent because the pKa's are so different. 15.7 to 50, that's um, bazillions of times weaker acid in butane than water. So if we do this, the base reacts with the solvent, and that's no good for our reaction. So this means that in water, the strongest base that we can use is hydroxide. And that might sound okay from a general chemistry perspective because hydroxide is a strong base. But if we look at our pKa chart, all the bases stronger. So there's hydroxide. All the bases stronger than hydroxide are those below it. And that's quite a few. So none of these bases are acceptable for use in water because they will react with water and generate hydroxide. And then hydroxide is the base that's in solution. So it would be overkill, essentially. And if you're wondering about the lithium here, that's going to be associated with the hydroxide And so when you do this reaction, you get lithium hydroxide. Really expensive. Hmm? Yes. So this is butane, which is just an alkane. And so when we look on the pKa chart, um, there's an alkyne. Really, all alkynes have a pKa of roughly 25. Alkenes, 44, 45. And then alkanes here. So this is ethane, but you can extend this to really any alkane, or for example, if you have a functional group that's really far away from the alkane that you're looking at, and we can say that this is essentially equivalent to ethane for purposes of determining the pKa. In the same way, amines, which are kind of like ammonia, where H could also be R in some cases, have a pKa of about 38. So we're just estimating. All right, so that's the case for bases, but I said the same is true for acids. So the acid cannot be stronger than the conjugate acid of the solvent. So this example I'm going to show you here probably makes a little more sense, I think, or will look more familiar to you. And that is using sulfuric acid as an acid in water. So in the same way where when we add butyllithium to water, we should at least see if this reaction is reasonable in the forward direction, which it is based on pKa. So let's do the same thing with sulfuric acid in water. Set up an acid-base reaction and see if the forward or reverse reaction is reasonable. So sulfuric acid is going to be our acid. Water will be our base. So we'll have a conjugate acid and a conjugate base. And don't get, scared by the fact that these are inorganic instead of organic. The rules for Bronsted-Lowry acids and bases are still the same. So an acid is a proton donor and a base is a proton acceptor. So well, these should be backwards, sorry. Okay, so the acid donates a proton to the base. All right. So that means we're now at HSO4 minus, right? That's sulfuric acid minus an H plus. And then water plus an H plus is H3O plus. So compare the two acids. Let's see. Okay, sulfuric acid, way up here with a pKa of -9. Our other acid is not water, but H3O plus with a pKa of minus 1.74. Higher pKa means a weaker acid. And so the equilibrium lies on the side with the weaker acid, which is there. So that means when you dissolve sulfuric acid in water, this reaction happens. You get H3O plus, right? This is how a strong acid works. It dissociates and becomes and gives you H3O plus. And so this H3O plus is the active acid in aqueous sulfuric acid. And so by extension, if you start with pure sulfuric acid, concentrated sulfuric acid that has a pKa of -9, and you put it in water, you get H3O plus. Now the pKa of your quote unquote sulfuric acid, your dilute sulfuric acid, is just minus 1.74. And so, for example, if you need a really, really low pKa to do your chemistry based on whatever acid you're trying to, or base you're trying to protonate, you may not be able to do this if you have water around because it will convert your sulfuric acid into the weaker acid, H3O plus. Okay, so the acid you use cannot be stronger than the conjugate acid of the solvent, or if you do use it anyway, you're essentially going to weaken your acid slightly, which generally speaking, we're okay with in the lab when we're using sulfuric acid or hydrochloric. So I mentioned briefly about with the whole butyllithium thing, how the lithium, let's see, the lithium stays around, but it just instead of going with the butyl anion, it ends up with the hydroxide. So when we have well, I'm going to say negatively charged ions, but right, ions always have to be in pairs. Negatively charged ions, which we're going to generally see as bases, right? Like hydroxide. Always have to have some sort of cation with them. And you could say that the opposite is true. If you have a positively charged ion or an acid, that always has to be accompanied by an anion. And so that cation, probably in general chemistry, you called it a spectator ion. A lot of times in organic, we call it a counter ion, but it means the same thing. Either one is wrong. So that means that if we have a reaction, and this one is going to look more like what we've been doing. Oh. So we might write something like this, and clearly we have two anions, one on each side of the equation, that are naked and don't have a cation with them. But of course they do, we're just not drawing it. And so really you could use anything. I don't know, maybe sodium is a common one to use. And so how we would write this reaction in kind of a more inorganic general chemistry looking way would be like this. So from the first drawing, we can more easily see what's the base acid conjugate, acid and conjugate base. Because we can see the charges, we can see the proton that has moved. There. But in the second equation, it might not be quite as easy to spot, right? And so this is one of those cases where you'll need to be able to see in this bottom equation that the counter ion is Na plus. Now, the most common sort of cases in which you're going to see this are, things like sodium hydroxide, where really what we care about is that it's hydroxide. The same would go for sorry, that's a double bond. There we go. This molecule, sodium benzoate, we've got a sodium there on the end, and this is essentially going to be equivalent to that. We could also have, let's see, something like NH4Cl. Actually, let me call it in Me4Cl to show which is the organic group. And so it's not a coincidence that I initially said NH4Cl. That is equal to NH4 plus and Cl minus, right? So in the same way, we can split up that, and then even further, for methyl groups on a nitrogen. That's what we're going to be looking at coming from there. Trying to think of other examples. Um, so the main thing is you'll see this happen with is um, bases, which are really salts, having some sort of alkali metal cation. It could be sodium, it could be potassium, it could be lithium, rubidium if you really want. I don't know. Um, but it's important that you can see uh, these cations and note that they aren't really important for the chemical reaction. They're just spectator ions. And further, a good rule of thumb is um, if you're able to draw the mechanism for the reaction, the mechanism is not going to involve that counterion, right? So when we have um, acetic acid reacting with sodium hydroxide, we draw the mechanism. Our base deprotonates our acid. And there's no arrow going to or from the sodium. It's just hanging out. Okay, so if we wanted, we could just not write it and no one would be the wiser. Of course, the problem is you can't just go into the stockroom and grab a bottle of OH minus. It doesn't work like that. You've got to have something to counteract that ion. But generally speaking, and there are exceptions to this, but generally speaking, it doesn't really matter what the cation is. Sodium hydroxide is cheaper than potassium hydroxide, so we use it unless there's a specific reason to do otherwise. As far as writing something like this on an exam, um, I'm not going to require you to write the counter ions. But if you start writing them, then you got to keep it consistent and write them throughout the rest of the problem or whatever. Okay, last little section, and this is pretty brief. Um, all throughout this chapter, we've been talking about Bronsted-Lowry acids and bases. So as a reminder, Bronsted-Lowry acid is a proton donor. And a Bronsted-Lowry base is a proton acceptor. The Lewis acid-base definition is broader than the Bronsted-Lowry definition. Um, and because Bronsted-Lowry acids are so common, and not that Lewis acids and bases aren't common, but just sort of the the language of chemistry. says that if you just say acid or base, you're talking about Bronsted-Lowry. There's a reason we spent like 3 days talking about Bronsted-Lowry and 5 minutes talking about Lewis. So if you're talking about a Lewis acid or a Lewis base, you have to use the qualifier Lewis in order to denote that you're talking about something slightly different. Okay, so the actual definition of Lewis acids and bases. Lewis acid is an electron pair acceptor. Okay, so careful with the acceptor being a base versus acid for the two different definitions. So that's something you got to be careful with. And a Lewis base is an electron pair donor. Now, these are really, really different definitions. Occasionally, one compound will be both a Bronsted-Lowry base and a Lewis base, or a Bronsted-Lowry acid and a Lewis acid. But it's quite common for them to not have too much relation to each other. So it's really sort of like a completely different concept than acids and bases as we typically think. Lewis acid-base reactions don't require proton transfer. And when you're drawing the mechanism, usually there's just one curved arrow rather than two in a proton transfer process, which is Bronsted-Lowry. Okay. So the product probably looks kind of strange, and that's okay. It is kind of strange. Um, but we can use the product and the new bond that's been formed to figure out which is our Lewis acid and which is our Lewis base. Now, just looking at these two compounds, which one of them do you think is a base? Just without thinking too hard about it. Ammonia, right? Ammonia we know is a base. Bronsted-Lowry base. In this case, it's also a Lewis base because it's donating an electron pair to the boron to make a bond between the nitrogen and the boron. And that gives us this bond in the middle. Nitrogen has 4 bonds and no lone pairs, so it's positively charged. Boron, a little harder to determine. But if you remember, boron is one of the elements that can form a sextet. That'll explain why BF3 is a neutral molecule. And so boron with 4 bonds has a minus charge. We don't really see a lot of boron in organic chemistry, but this is one of the cases. Okay, so ammonia is our Lewis base. And so BF3, boron trifluoride, is our Lewis acid. So the electrons are starting at the Lewis base, the lone pair of the nitrogen, and going toward the Lewis acid, the electron pair acceptor. Okay, another very strange looking reaction. I think you're seeing a trend here. In both cases, the products here have a positive and a negative charge right next to each other. In both cases, we're using a bit of a conspicuously weird element, boron here and aluminum here. Not a coincidence. And additionally, in both cases, we've got a lot of halogens on that boron or aluminum, right? So can draw a mechanism for this that's the same as above. Lone pair from the oxygen attacks the aluminum to form that bond. And so the electrons come from a lone pair on the Lewis base and attack the Lewis acid. There's no conjugate Lewis acid or conjugate Lewis base. Just it didn't really work like that. Because in a reaction like this, this is a synthesis reaction. You're combining two molecules into one. In particular, Lewis acids are the best way to put this is BF3 and AlCl3 are like classic Lewis acids. Um, Really, their only purpose in life is to be a Lewis acid, and that is a common thing with Lewis acids. Is like they're their own sort of category almost. Uh, Probably the most common Lewis acid is MX3, where M is a metal like aluminum, and X is a halogen, right? So BF3 and AlCl3 both fit that scheme. I know boron isn't technically a metal, but organic chemists are weird and we consider boron metal. So that's just something that you might see fairly often. And then Lewis bases are really, really broad. It's almost like the opposite. Lewis acids tend to be a very kind of a small group of just a few different really common compounds that are used as Lewis acids. Then Lewis bases can be anything with a lone pair, basically, right? Because it's an electron donor. And well, any lone pair can potentially do a reaction like this. If it finds a something that's electron poor, like a Lewis acid, um, one of the reasons they're electron poor is because right the like the inductive effect that we're using to determine acid strength. If you have a lot of halogens, right, that pulls electrons, they're electronegative, so that pulls electrons away from the central atom. Okay, if we have a boron atom that's already just got 6 electrons, or an aluminum atom that's already just got 6 electrons, and we add halogens to it, continue to pull those very few electrons away from it, it really, really wants electrons. And so it really wants to accept an electron pair from a Lewis base, an electron pair donor like ammonia or a carbonyl compound. This kind of thing down here with the oxygen aluminum bond, we'll see again come up in organic 2. And they're useful for a couple very specific kinds of chemical reactions. Okay, so that's basically all I want to say on Lewis acids and bases. It's really kind of simpler just because there's one arrow and you have electrons that are moving and no protons. But we won't see them quite as much in organic. Questions on Lewis? It's like, no, get me out of here. Spring break, please. All right. After break, we will start talking about nucleophilic substitution reactions.